Good morning. I'm Michael from University of Bremen, and I would like to talk about our paper called Get a Grip, Introducing Variable Grip for Controller-Based VR Systems. So this started off as part of a research project where we want to teach robots how to help us in the house. And for this, we need to show them how to. Otherwise, they don't just know. And we want to do this by demonstrating it to them. They imitate it, and they learn it from us. So I tested this kitchen simulation here, where the goal is to instruct robots how to help us set the table or cook. And I was facing some different problems. As you can see here, I struggled with putting glasses into an upright position. We certainly have some other issues that we have to tackle here, but that should not be our concern now. There will be more papers. So how can we do better in real life? We can let objects swing in our hands so it automatically aligns. We can hold them firmly, but we can also just let it loose. And then it adjusts according to gravity. Please, if you have any cup in reach, if you brought a coffee, try it out yourself, because we do that very unconsciously all the time in everyday life, and people keep telling me, no, I don't do that. And then they experience it, oh yeah, actually, if I pick it up from the floor, I do. But at the moment in VR, this is not happening. We have three ways of coping with it. Either when we have that bad angle here, we twist our wrist, which is very uncomfortable and cumbersome. It feels wrong putting it up that way. Or secondly, we regrasp the object. We put it down and pick it up again. Well, if we can, if there is a free surface, right? Or thirdly, we throw and catch. But that needs skill. That was not the first time I took this video. So it's uncontrolled, it's unreliable. Objects tend to fall down. And these workarounds we refer to as clutching, which is, quote, the releasing and regrasping of an object in order to complete a task due to not being able to complete it in a single motion. So we want to show robots how to cook or set the table, but I do not want a robot to learn from me how I throw around glasses in my kitchen to rotate them. So we need to reproduce the real-life behavior here. Our idea is to simulate human capabilities of verifying how firmly we grip something so that we can hold objects both firmly and switch to loosely. We devised and evaluated a grasping system featuring variable grip firmness, and we wanted it to be as accessible as possible, so no fancy proprietary hardware. It works for any controller-based VR system. And as a proof of concept, we implemented it for the HTC Vive with its wand controllers. And since we're going to talk about buttons that have given names, you know, the trigger, the two smaller buttons on the side of the handle are called grip buttons. We identified a couple of design properties, as the object interaction can be designed in so many different ways, including temporal scope, what buttons we use for grasping and for adjusting the grip, the default grip firmness, if it's initially firm or initially loose, the anchor point, so where the object is attached to the controller, gravity, whether the center of mass is adjusted or not, and the visual representation of hands or controller. So don't try to understand this slide, it's just to give you an idea how many combinations we suddenly have, and this overview does not even include temporal scope, visual representation of the hands, center of mass adjustment, or the semi-fixed anchor point. So before we selected a mode to quantitatively test, we conducted a pilot study first and selected these 5 diverse modes in a qualitative study. It was an exploratory semi-standardized pilot study within subject design. We had 4 participants who tested all the 5 modes. The task was to move objects around from the table here to the shelf on the opposite and rearrange them there. Here, the user uses an initially loose mode with a fixed anchor point. We asked them to think aloud, to share their thoughts during the experiment. It took them about 45 minutes, and with that control panel in the middle, they could switch between. I'm not going into depth here with the results. There is qualitative data with quotes in the paper. We learned a lot about the anchor points and the buttons, and that gravity and visual reference can be very helpful for our purpose here. And also we learned there are pros and cons for all of the modes that we put to the test here. There is no clear winner that we can just put to the test now in a quantitative comparison. So we wanted to select promising interaction designs to compare performance, task load, and usability factors. Hence we pulled up our matrix again, and with the insights from the pilot, we then devised 4 promising new interaction modes that you can see here. Please note the color code as they will be marked in the same colors for the results. Here's a better overview. So we have 2 modes with variable grip, modes A and B, and we have 2 modes without variable mode for, grip firmness, modes C and D that we refer to as baselines. Mode C has an always firm grip, and mode D is always loose. We always grab things with the trigger, and while in mode E, you have a loose grip by default in the beginning, you can change the grip firmness to a firm grip with pressing the grip buttons. And in mode B, you grab firm by default, and then you can let it loose by loosening the trigger. The task in the main study was to move glasses from a start to a target position, and we asked our participants to do this with 15 glasses per task. We had 4 tasks, 2 horizontal, 2 vertical, and we tested 4 interaction modes. So every participant had 240 glasses to move, and with 28 participants, that makes a total of 6,720 glasses. The order of the modes was randomized, and after every sequence, we asked our participants to fill in a questionnaire and conducted a semi-structured interview in the end. So let's look at the results. First, the usage of the grip variability. The behavior couldn't have been more diverse. Some participants varied the grip on every single glass, others on no single glass. Overall, for 3 out of 8 objects, the grip was adjusted. Just take a glimpse at this plot to see the modes A and B have been used quite differently. In terms of performance, it comes to no surprise that adjusting the grip takes a bit of time. In our case, this was the quarter of a second, so about 10% longer than the firm baseline mode C. In terms of precision, there is no overall difference at all, only if we isolate horizontal tasks. As you can see here, then we have a significant difference between the groups, but only with a very small effect size, so we can neglect that. Clutching was surprising to us what we observed here. We hoped there would be less clutching. We observed a tendency towards more clutching in the variable modes. Only a tendency here, but the effect is stronger when we look at whether a grip was handled on an object or if it was handled with a uniform grip. If you want to exchange theories how that comes, please come talk to me later. At the moment, the best guess is there is a very steep learning curve that we observed, but that's certainly up for discussion what happened here. We also looked at the task load. We conducted a NASA raw TLX and didn't find any significant difference overall. Only the factor frustration was significantly lower for the modes with variable grip. And we looked at usability. We tested 10 usability factors that aggregated to that overall value here, where mode A was rated the best overall with 8.1 score compared to 6.8 in the baseline modes. And also variable modes significantly performed better in terms of satisfaction, control, intuitiveness, realism, comfort, difficulty, and cumbersomeness. And finally, I want to point out that when we afterwards asked the participants, if you would have to repeat that with another 240 classes, which mode would you pick? That 2/3 of our participants would prefer one of the modes with variable grip. So I would like to conclude. We propose adjustable grip firmness for VR to enable interaction that better corresponds to object manipulation in real life. And I have 4 takeaway messages for you. Variable grip is 10% slower, and it's not always needed. Hence, just use it wisely. But we can also see that it can enhance usability, improve realism, and reduce frustration, because it better resembles what we do in reality. And it was preferred by most of our test users. And lastly, and I know this is an annoying one, but it depends. We did not find an ideal solution here. It's not going to be the new standard, right? But it indicates immense potential for a variety of applications. So, for example, it's great when we want to instruct robots how to help us. So interaction is another step closer to real reality in VR now, but it's just the first step. So where can we take it from here? It would be good to also look at other object classes, not only rotationally symmetrical drinking glasses. And we can look at more complex tasks, so tightening screws or balancing objects or more delicate manipulations. And we should do a long-term investigation and see how people get accustomed to the system. Also, it would be intriguing to look at deformable objects and how they react to squeezing. And finally, we should transfer it to other systems, like Oculus Touch controllers, but maybe also to augmented or mixed reality or systems without any controllers. And I can't wait to get my hands on these. These are the Valve Knuckles that are under development at the moment, so they're not publicly available yet, but they're waiting for me on my desk. And the nice thing is that a user can use the grip as input, as there are sensors built into the handle that react to squeezing. So can't wait to test it again with these. Now, if you have any questions, I'm very happy to answer them. Thank you.
Hi, Regis Copper from Duke University. Nice, very nice work. So I have 2 questions. One is regarding your experiment. You didn't require, I mean, the orientation of the object was the same from the origin to the target. So there wasn't a whole lot of, naturally there wouldn't be a whole lot of clutching without the variable grip. So why did you choose that? Was there a design thought for that, or was just how you did it?
There wasn't so much incentive to clutching, that's true. We want to keep the task as simple as possible to start with, to get a first comparison. And then in our own experience in pre-studies, we noticed that only the movement from down here to up there would give already such an uncomfortable angle in the wrist that would be motivation enough. And then we also wanted to have the comparison with horizontal tasks. Okay, but there's a lot to follow up there, so thank you.
The other question is just on the design of the technique, but it seems like if you have the variable grip, are you able to use the surface where you're dropping it as a support, because that could eliminate the risk for dropping it, or like, you know, when you drop it in a wrong orientation, it bobbles. And so if you have the variable grip, are you able to just use the surface where you're dropping it as support? I don't know if you understand.
To have the physical resistance to balance it out, you mean?
Yeah.
Yeah, that would be possible.
Okay, sure. Cool. All right, thank you.
Thanks.
Very fast. Really nice work. I'm wondering if you have thought about using this metaphor also to interact with physically based simulations. You're simulating physics to a certain extent, right? And you could really, if you would have a physics systems physics system in your VR application, you could interpret this really as a force, right? Also to push against other things and so on. Have you thought to, apply your approach to input force in principle, right? The grip force into the system to interact with the physics-based simulation?
Absolutely, yeah. That will be very interesting to look into the future. Thank you.
Thanks.